students, I am Professor Isha Medirata from LG Institute of Engineering and Technology. We have started with the chapter Electronic Materials, and in the previous video we discussed a topic that is density of energy states. In today's video we are going to discuss a very important topic which is known as the chronic Penney model. What exactly is the chronic Penney model? Who developed the chronic Penney model? It was developed by Ralph Chronic and William Penney. They are the two physicists who proposed this model. What is chronic Penney model? This is a simplified model for an electron in one-dimensional periodic potential. I'll be discussing later what exactly is one-dimensional periodic potential. See, what is the use of chronic Penney model? It explains how band structures are obtained, particularly using Schrödinger equation. Next, it explains how periodic potential gives us energy bands and band gaps, how the concept of effective mass is defined, and what is EK diagram. So all these parameters can be determined with the help of chronic Penney model. So this is the use of chronic Penney model. Next, what are the points which lead to chronic Penney model? What was the need of defining such a model by Ralph Chronic and William Penney? So we have seen in the quantum theory that electrons in a metal experience a constant potential. This is what we discussed in our previous video, that if you have a cube and if you consider a particle, say an electron, it constantly moves within the cube, but exactly at the boundaries the potential becomes infinity. So according to quantum theory, we say that within the box, the potential is zero, that means constant. This theory, the quantum theory, it failed to explain the difference between conductors, insulators and semiconductors. Also a topic called positive Hall coefficient of metals. So some parameters were not explained by the quantum free electron theory. So to rectify these issues, what was proposed? That instead of a constant potential, there is a periodic potential which the electrons experience. Now, how does this periodic potential come? It is because of the particular arrangement of the positive ions. The lattice arrangement yields periodic potential. Let's discuss the potential in a lattice. So, in a real crystal, the periodic arrangement of positive ions is there. And through this arrangement, the electrons will move. Potential of electrons, exactly when it is in the range, in the line of the positive ion, the potential will be zero. When it moves and it is exactly between the two positive ions, the potential will be maximum. Let's have a look at this diagram. In the diagram, you can see the arrangement of positive ions and there is an electron which is moving. Now let me just make it very clear, the chronic Penney model deals only with one dimension. So you have to assume that either it is moving in x direction or y or z. So particularly the electron motion is considered in one direction only. So according to this diagram, exactly when it is in line with the positive ion, you have potential to be zero. Between the two, the potential is maximum. Let's see what the potential experienced by electrons is. So in this diagram, you can see the upper portion has simple one-dimension motion of electrons based on the concept that electrons have zero potential in line with the positive ion and maximum in between the two. Just look at the second diagram here, which indicates zero potential and then you have maximum potential. Then again zero and again maximum. Why is this periodic arrangement? Because the interatomic distance is fixed. The maximum potential the electrons have or achieve is denoted as V0. It have considered x-axis and V, that is potential, along the y-axis. So maximum is V0 and it is exactly zero where you have the positive ion. There was a difficulty in solving Schrödinger wave equation by assuming this periodic variation. Why? Because if you just look at the second diagram in this figure, what exactly happens? There is a constant variation of periodic potential. So it's constantly increases and then decreases. Again increases and again decreases. So between any 2 points, there is a change in potential. To rectify this problem, what Ralph Chronic and William Penney did, they considered only two values. One is V equal to 0. and other V equal to V0, that is maximum. So in the third diagram here, you can see the exact value of potential is 0 when it is at the positive ion site, and it is maximum when it is between the two. So we have V0 as the maximum value and V equal to 0 as 0, only two potential values. Next, solving the Schrodinger wave equations was difficult, and so the rectangular approximation was done. This is the same diagram like the earlier one, but here I have just mentioned the regions. You can see here 2, wherever the Roman letter 2 is indicated, it indicates the maximum potential V0, and in between them we have 1, that is a region with 0 potential. Now we can define Schrodinger wave equations only of two different regions. The Schrodinger time-dependent wave equation along the x-axis can be given by the equation d square psi by dx square plus 2m upon h cut square E minus Vx psi is equals to 0. This is the equation which we had discussed in the previous video as well. Here E is the energy of electron and Vx denotes the potential. In our case, we have two potentials that we have considered. Vx, one case we have considered 0. Vx in the other case we have considered as V0. So owing to this equation, what exactly happens? Now we can define the Schrodinger wave equations using only two regions, 1 and 2. 1 is the region where your potential becomes 0 and 2 is the region where your potential becomes maximum. So let's see how the Schrodinger wave equations are written. So they can be written as d square psi by dx square plus 2me psi by h cut square equal to 0. This is for a region 0 to a where we consider v is equal to 0. The second Schrodinger equation can be written as d square psi by dx square plus 2m upon h cut square E minus v0 psi equal to 0. Here v is not 0, instead it is maximum. This is for the region minus b to 0, or where we have considered the potential to be maximum. Now the solution of this Schrodinger wave equation can be derived using Bloch's theorem. No need to derive it, it's just an equation you need to remember. So the solution can be given as psi x, where psi is the wave function. Psi x is equals to e raised to ikx into ux. What is e raised to ikx? It is known as a plane function and ux is known as a periodic function. Let me explain you the difference between the two. Pertaining to our case, we can say that e raised to ikx is the plane function, say motion of electron, and ukx is the periodic function, say the arrangement of lattice. So if we consider the potential of electron, exactly at the positive ion site it has a different value, and exactly in between the two it has a different value, and this variation is periodic. So I say the potential is controlled by the atomic distance. So this is what exactly plane function and periodic function mean. If you use Bloch's theorem and if you apply all the boundary conditions, the actual solution we get is p sine alpha a upon alpha a plus cos alpha a is equals to cos ka. Your alpha is a constant which they had derived. What exactly is P? P is a term which is known as a power with which electrons attract the ions. The attraction should be minimum. If the value of P is very high, the electron won't be able to move. So it gives us a strength of attraction. If you just look at this equation, you can say that the complete LHS should be equal to cos Ka. That means I will say if I compare this equation, my LHS should also have the same limits as my RHS. We know that cos function has a limit -1 to +1. That means the summation of LHS, that is both the terms on LHS together, should have a limit -1 to +1. Next, what is done? A graph is plotted using this equation. Now you know that sin x upon x is a normal graph wherein we have sign variation as a function of x, and cos again is a simple graph. What is done, what is shown in this diagram is, it is the combination of p sin alpha a upon alpha a and cos alpha a. So summation of both of them is shown here, where I have plotted p sin alpha a upon alpha a plus cos alpha a on the y-axis and alpha a, that is variation, on the x-axis. we know that this LHS should be having the same limit as RHS, and we know that RHS is only a cost function which has the limit -1 to +1. Now when the graph, the summation graph is plotted, you can see it actually is a sine graph only. But what is the difference between a sinusoidal graph, cosine graph and this graph? We know that sine is a function which will always be 0 at the terms pi. Intervals of pi, sine function is 0. At the intervals of pi by 2, cos function is 0. But when you add both of them, I say sine pi is 0, but cos pi is not 0. So the summation will not be 0. Similarly, cos pi by 2 is 0, but sine pi by 2 is not 0. So summation will be non-zero, and this is what is seen in the graph. At all pi and pi by 2 intervals, you see that graph is not 0. But in the graph, you can say there are many regions which are beyond +1 and which are beyond -1. Right? Now, and that is what is indicated by the shaded portion in the diagram. Now let us see what are the findings of chronic Penney model. By plotting the graph, what was their conclusion? So starting with conclusion number 1. We know that permissible limit of the term on the LHS should also be +1 to -1. And by varying alpha A, we have plotted a graph. We have plotted a graph which is like this. Here what I have done, I have just shaded, just colored the portion which are apart from +1 and -1. So according to the diagram, you can see whatever is the black colored portion that is beyond +1 and -1. So this is what is known as the forbidden values. These are the values which are not acceptable. Why? Because they are not in the permissible limit -1 to +1. So these values of energy, they labeled as forbidden values. That is the reason we say that forbidden gap is an energy value which can never be occupied by electrons. And all the values which are in the terms -1 to +1 are known as allowed energy values. What was the second conclusion? If you say the value of P tends to infinity, that means if I write P as infinity in the equation P sine alpha A upon alpha A plus cos alpha A is equals to cos Ka, my entire LHS would be infinity. So I will be getting cos Ka is equals to infinity, and I will be getting only one value. So my entire spread reduces to one discrete value. And what if I say the value of P tends to 0? If I say P is equals to 0, I have cos alpha A is equals to cos Ka. So the graph I will be getting would be a cosine graph only. That means all the values are within the limit +1 and -1. That means that is no forbidden value, and this is a case. This second diagram is a particular case of metals. So this was just a glimpse of chronic Penney model. What was the need of defining a chronic Penney model? What are the uses of chronic Penney model? And what are the conclusions regarding chronic Penney model? Hope you have understood the topics discussed today very well. I will be starting with EK diagram in my coming video. Till then, take care. Thank you.